2010 E&M number 2. They've given us a circuit here with some resistors, some capacitors, and a switch that is open to begin with. What this means is that the bottom branch and the top branch are in parallel with each other. Notice that both of those branches contain a capacitor, and they tell us that the battery has been connected for a long time, so that means that both of those capacitors are completely charged up. Once the capacitors are completely charged up, that means the current through each branch is going to be 0. So the current through the 5 microfarad branch is going to be 0, the current through the 10 microfarad branch is going to be 0, and that means the overall current through the circuit, as measured by the ammeter, is also going to be 0. So I equals 0 to begin with. Now, as the two branches are completely in parallel, what this means is that the voltage drop across the 5 microfarad is 30 volts, and the voltage drop across the 10 microfarad is also 30 volts. So for part B, the charge on the 10 microfarad is going to be V times C, and because they are completely in parallel, notice they're in series with their respective resistors, but they're in parallel top and bottom. So the current being 0, voltage across each capacitor is 30, and they want to know what the charge on the 10 microfarad is, so that would be 300 microcoulombs. Well, what's the energy stored in the other guy? There are several variations on the energy in a capacitor equation. In this case, since we know the voltage across each capacitor, it's 30 volts because they are both connected to the battery. So the one side of the capacitor is connected to the battery, the other side is connected to a resistor, but there's no current going through the resistor. So effectively, the other side of the capacitor is also connected to the battery. So in the case of the 5 microfarad, well, we have 5 micro times 30 squared, and that gets us an energy level of 225 millijoules. Now we're going to close this switch. If we close that switch, now we're changing the nature of this circuit such that we have the 5 microfarad in parallel with 40, and then the 10 microfarad in parallel with 20. So let me redraw that circuit just a little bit. So we have our 30 volt battery. And then we come up here and we have a choice between 5 microfarads or 40 ohms. So we have a choice. And then, after that, we have another choice to make. Oh, and then the ammeter is there, effectively. All right. The steady state current through the battery, once we've reached that. Now, when this guy is all the way charged up, he effectively is removed. And when this guy is all the way charged up, he's effectively removed. So the current goes through the one resistor, then goes through the other resistor, and then goes through the ammeter. So for part D, our total resistance is going to be 40 ohms plus 20 ohms is going to be 60 ohms. And our current from Ohm's law is going to be the battery over the total resistance, which is going to be 30 over 60, also known as 0.5 amps. Don't forget the units. These are numerical problems. All right, part E. What is the final charge on the 5 microfarad capacitor? Okay, so that 5 microfarad capacitor is going to be in parallel now with just the 40 ohm resistor. So whatever the voltage drop across the 40 ohm resistor is, it's going to have the same one across the capacitor. So VC equals VR. VR is going to be the current times the resistance, and that current, once both of the capacitors are fully charged up, those two resistors are going to be in series, so the current through one is going to be the current through the other. So 0.5 times the resistance of 40 ohms gets us a voltage of 20 volts. That's the voltage across that 5 microfarad capacitor. So the charge on it is going to be those 20 volts times 5 microfarads, which gets us 100 microcoulombs. All right, part F. Energy dissipated in the 40 ohm resistor. So I'm going to have to come over here for part F. Remember, power is I squared R, and power is also energy dissipated over time, or energy used up over time. So what they want is the energy dissipated, so we're going to have to multiply that by time. So energy is going to be I squared RT. This is going to be 0.5 squared, and they said that they want the 40 ohm resistor, and 1 minute, well, that's not the proper SI unit. It has to be in seconds, so we're going to need 60 seconds here. And once we figure that out, that will be 600, and this will be in joules.